All right, we're going to go ahead and get started. Quiet down, guys. All right, so today, two quick announcements. The first is that I think check the syllabus. I think it's next Wednesday. Your recitations is the first quiz. So generally, the sort of rule that I have in terms of quizzes, if you sort of ask me, oh, what's going to be on the quiz? What's going to be on the quiz? The sort of rule that I generally go by, and I think just to sort of prepare for, is that I like to give everybody a weekend to prepare, right? So for those of you that are taking the quiz on Wednesday, for example, you will be responsible for everything through today. And certainly then the people that would be the following week that would get the extra weekend, you'll certainly be responsible for this material as well, but there may prop up some of the material from next week as well. So just be prepared for that. So that's generally what I like to try and do. Again, the emphasis, though, will be on the material through today. It's just that what I don't want is for the people that are the following week to not be catching up on material and then be behind for the exam. So if you're that, so basically for everybody that's this upcoming Wednesday or whatever, it's going to be everything through today. The following week, you may see some stuff from that week as well, but the emphasis will be on this material. I will also say that just sort of so that you know what to prepare for, I put a very large emphasis on mechanisms. So any mechanism that I show you guys, there's a very good chance that one of those will show up on your quiz. So make sure that you can draw every mechanism of every reaction that we've seen. It might not be packaged, right, exactly what we see here, but it will be that type of mechanism question. You guys should all start, hopefully by this point you're okay at synthesis. You can expect to see a synthesis question on the quiz as well, and then there'll be some other question that'll keep you on your toes. But so just make sure that you're, if you need something to sort of drive you to prepare mechanisms, know all the mechanisms, and again, synthesis. And remember, the whole idea with synthesis is that it's not just going to be reactions that we've learned this semester. A synthesis problem, they'll be rather short. There could certainly be longer ones, for example, on the exams, but on the quizzes, generally, I come up with a synthetic sequence that's usually about 3 steps. If it takes you 4 or 5 or 6 steps, that's fine, but they don't need to be super long. They can be. You're not going to get penalized if you have too long of a synthesis. But again, the reactions may pull from reactions from organic ones, so you're sort of responsible in that way for knowing the reactions of organic ones, specifically within the case of mechanism problems. Okay, so with that, we've sort of finished, for the most part, carbonyls. There are certain elements from within carbonyl chemistry that I might discuss, at least stuff that was in that chapter, I might discuss as we move forward in a context that I think is perhaps more appropriate. And I think there's a sort of a logical progression, right, from carbonyls, certainly to carboxylic acids. Right, and so when we're talking about carboxylic acids, these are when we talk about carboxylic acid, certainly these are very important functional groups. The name sort of implies, again, their sort of behavior. Again, these are acidic because in the presence of sort of moderate bases, what can happen, right, is that you get the carboxylate. Again, simply through Bronsted acid, Bronsted base mechanism, which you should all know very well. And so you get to the carboxylate. And again, the whole reason, you spend a lot of time in Organic 1 discussing about factors that can stabilize charges. And so at this point, you guys should all sort of understand that the reason why this is acidic is because the conjugate base, which is in this case the carboxylate, right, is well stabilized through resonance. Right, and so in essence, what happens, right, is that negative charge is spread out over 2 oxygens, right? So again, anytime you're sort of thinking about stability of charges, resonance is oftentimes one of the most important sort of aspects within stabilization of cation or anion sort of forms. Now, again, I don't want to spend too much time. The book talks a little bit about different types of carboxylic acids, but certainly the pKa values, or relatively how acidic a carboxylic acid can be, is going to be dependent upon other factors in terms of the R groups. And so, but in general, when we talk about carboxylic acids, the pKa values are generally anywhere between sort of 0, I would say, equals about 0 to 6. So there's a fairly decent range there. Something like acetic acid, for example, which just has a methyl group there, has a pKa of, I think, about 5. Right, and so this would sort of represent one of the sort of less acidic of the carboxylic acids. And then if you have something, say for example, one of the sort of stronger examples of carboxylic acids is trifluoroacetic acid. So this is acetic acid. Right, one of the more acidic acids that we'll see on occasion is trifluoroacetic acid. pKa of about 0. Okay, this is often abbreviated TFA, so it's just trifluoro, right? Trifluoroacetic acid. The name should make sense. TFA is you know, there's other things such as benzoic acid that we'll see on occasion, which has pKa's around 4, and again, you can see minor changes based upon the substitution patterns. But again, this sort of illustrates the sort of range of acidity that you could perhaps have. TFA we'll see maybe later on when we start talking about proteins and peptides in particular. It's a really valuable acid in part because of the fact that it's more acidic. It's also actually more volatile, even though it's heavier, it's more volatile. Fluorine-containing molecules with carbon-fluorine bonds tend to be more volatile. And so what's nice about this is I think the boiling point is like 60 or 70 or somewhere in that range, whereas acetic acid is like up over 100. And so what can happen is you can actually rotovap this off. Say, for example, you can use it as solvent, and it's sort of pretty useful. But anyway, I don't want to spend too much time discussing the different types of acidity associated with them, but you can sort of tell that if you put substituents over here, again, the whole reason why this is more acidic is why? Yeah, inductive with electron withdrawing. Again, you can sort of see trends, for example, with aromatic groups, right? So if you have, say, for example, a substituent on, so if you have something like benzoic acid, the pKa, again, I think is somewhere around 4. But again, as you begin to put substituents on there, that can change a little bit, anywhere between, I think, nitrobenzoic acid is somewhere in the 2 range. And again, if you put something like hydroxy there, actually it's not going to change it too much. It'll be in the 4.5 range as well. So again, this is just the point that I wanted to make. Again, carboxylic acids will have varying levels of sort of pKa, but it's just sort of safe to assume that they're in this range. And so when we start talking about reactions, this certainly isn't, when we talk about things like carboxylic acids, we're certainly not in the same vicinity as something like sulfuric acid, which has pKa's in this sort of negative area. And so you're not going to treat something with, say, for example, acetic acid and suddenly protonate an alcohol or something like that. It's not quite strong enough to do something like that. But it is a mild acid, and certainly if you're in environments where you have something like an amine, right, so amines are sort of mild bases, those will certainly deprotonate them. From a mechanistic standpoint, I think that it's important to recognize that that acidity is often involved in a lot of the chemistry that we sometimes see, though. And so one of the first reactions that I want to show you guys is a kind of interesting reaction. I actually went through this in my office hours the other day. And this is a molecule known as diazomethane. And one of those sort of, at least, it's actually technically a challenging reaction to run, in particular because diazomethane is explosive, so you need to use like special glassware, for example. But in terms of technical nature of this reaction, it's actually a very clean reaction. And it's a way that people can take things like carboxylic acids and put methyl groups on them, so you can get the methyl group. And the first step in this reaction, in terms of the mechanism of this, is, again, sort of acidity and relative acidity of the carboxylic acid is heavily involved. So if you were to start to think about how this mechanism might take place, this would actually be a pretty good sort of, and I would say moderately challenging mechanism problem, first and foremost, because at the onset, what you have to sort of recognize is sort of what the base involved in this process might be. And when you look at this diazomethane by itself, right, I think everybody's first instinct might be to take a look at that nitrogen and assume that perhaps that negatively charged nitrogen, right, might be the most basic component in this, right? And so that might be the sort of first instinct. But again, when you're doing synthetic organic chemistry, you sort of have to become a chess master in a way, and you have to think of sort of a few steps ahead. And when you look at the sort of product, what you notice is that there's a CH3 in that product, right? And you look at the reagent, and over here you have a CH2, right? And so thinking ahead a little bit, you may want to start to think, well, okay, I can protonate that nitrogen, but if I look at what the product has, there's this CH3 in it, and so it might be valuable if I could actually, instead of protonating the nitrogen, maybe I could protonate the carbon, right? And then you sort of look at this molecule, and what might you recognize about this compound? Is there another way that I could draw that molecule? Yeah. Yeah, so there's a resonance form involved here, right? And that is one in which now we can push that negative charge over the carbon. Again, remember this is sort of an owl type shift, so this is one of the things that you guys got to get comfortable with, pushing a couple electrons simultaneously. But what we're effectively doing is the lone pairs are going to this nitrogen, right? We can't keep 5 bonds on that nitrogen, right? We'll break from the octet rule, so when we push them there, and this is the same thing as any owl anion oftentimes that we have, you got to kind of push the 2 electrons simultaneously, which means that once that has 5 electrons on it, we have to immediately break an additional bond, and that's going to be over here to put the negative charge here. Okay? So once we have this new resonance form, now we can start to think about what would happen if we deprotonated the carboxylic acid at this step, right? So again, we have that lone pair there. We can go ahead and deprotonate carboxylic acid. Right? And then the mechanism starts to become very easy, because now we've got a carboxylate that has a negative charge on it. We've seen carboxylates in the case of substitution chemistry, for example, being good nucleophiles in a way. And really what we have is, and again, we'll see these types of nitrogen leaving groups, particularly when we get to aromatic chemistry, but you see basically this cation, this positively charged species over here with a leaving group, right? We've seen leaving groups be bromide and chloride. Well, you can't get much of a better leaving group than nitrogen gas. Okay, and so what's going to happen here is we're going to attack. It's going to make that compound. And again, it's driven largely by the release of nitrogen gas. Again, we saw nitrogen gas is not really a leaving group, but kind of an elimination product previously when we discussed the Wolff-Kishner reduction, right? And so this is an example where the nitrogen previously had a negative charge, in this case, and have a positive charge, and again, sort of driven by that leaving group. And so here's just an example of one mechanism of a reaction on an ester, in which case you can take advantage of the acidity of that carboxylic acid. Okay. Now, again, we'll see more chemistry down the road where we take advantage of that carboxylate, especially when we get to things like amino acids. We'll see a little bit more of that. But the sort of one of the things that I think is worth sort of mentioning when we get to things like carboxylic acids, right, is that they are inherently one of that class of carbonyl compounds that we've discussed. And so there's a lot of chemistry associated with carboxylic acids, which are going to be very analogous to the reactions that we've seen previously. Right? And so, as an example, right, previously we saw a mechanism, right, where if you take a carbonyl, right? And you take this carbonyl and you treat it with acid in the presence of, say, methanol. What's the product that we're going to get out of this? Hemiacetal would then go to a full-blown acetal. The hemiacetal is the sort of intermediate. So we'll get the acetal, right? And again, the mechanism through which this process takes place, if we remember, right, is it starts with protonation, right, of this carbonyl, which is going to activate the carbonyl for methanol attack. Now, it turns out that if we have a carboxylic acid, through a very mechanistically related process, right, you treat this molecule with acid and some alcohol, such as methanol. What ends up happening is we don't get to say the acetal, but actually what we get to is an ester. So another way to make an ester, aside from the diazomethane reaction, would be to simply take this molecule and treat it with acid in the presence of an alcohol. Again, this takes place fairly quickly. Okay? That's what we're about to discuss in a second. Okay, so if I were to ask you, who asked that? So if I were to ask you what the first step in this mechanism would be, what would you assume? Protonation of what? So we got two options. Okay, I'm hearing a lot of show of hands for carbonyl, show of hands for OH. Great. Okay, so about probably a third of you said this OH. And again, you might be able to get a much more direct reaction if you protonated, say, for example, this and treated it as a leaving group, similar to, say, for example, acid-mediated esterification reactions that we saw under the ether chapters, right? You take a couple alcohols, you treat them to acid, you can get an ether. But in this case, what we're going to do is we're going to protonate, the majority was correct, and the first step is going to be protonation of that carbonyl. Why do you think that this somebody that raised their hand discussing and said the carbonyl, yeah. Yeah, right? In this case, you don't really have a resonance form where you can sort of stabilize that. You might imagine a resonance form, I guess, where you sort of broke that bond. But again, now you're sort of, it's not really a resonance form, sort of like you're making a couple of different molecules. It is a resonance form in a way. But this one, again, you have this ability, right, to resonate into the other oxygen. In the same way as we saw the acidity delocalizing that negative charge throughout the two oxygens, in this way what we're doing is we're effectively delocalizing the positive charge through those oxygens. So yeah, so the first step, generally when we're talking about transesterifications, is what this would be called, is to protonate the carbonyl, right? And once we do that, now in the same way that protonating this carbonyl allowed for the attack of the methanol, the same thing is going to be able to happen here, right? It's the methanol is going to attack. Okay. When you look at this, what we now need to do is we can go the reverse direction and lose methanol, or, right, because again, every reaction is reversible, so in principle we could just push the reaction in the reverse, but obviously that's not going to be productive. So what we're going to need to do is do a proton transfer. Again, this doesn't necessarily have to take place. I'm sort of just showing it to say forward space in terms of intramolecular process, but certainly things like the methanol around there could be protonated to help assist this process. But the idea here is that we're trying to get water to be a leaving group, and so right, and so now instead of this sort of NeOH plus, now we can actually get the H2O plus as the leaving group. Okay. Again, this is going to get to sort of drawing this on its complete. Again, we still have that proton on there. And again, this process is going to be catalytic in sort of acid, and so at some point we're going to regenerate that acid source. Again, it could be the counter ion. You could imagine having the carboxylic acid sort of deprotonate it, but something's going to come in here, right, deprotonate that, and that's going to lead to the product. Now, similar to what we saw with acetals, right? I'm not going to spend time doing the exact identical reaction in the reverse, but again, as we sort of stated, every reaction in this sequence can, in principle, be reversible, right? And so the synthesis, the sort of transesterification, taking a carboxylic acid, right, and making an ester, we're sort of driving this process by what? With Champollieu's principle, right? We're going to have an excess. So, for example, if you have this and you're running this in a solution of methanol, well, then you have a lot more methanol. Again, at this step here, we're generating water, right? And so at that sort of step there, if we have a lot more methanol than water, then it's going to drive the reaction forward. Again, sort of general chemistry sort of concepts. Likewise, right, if we want to go in the reverse direction, all we're going to do is instead run the reaction. Instead of doing methanol, we take this compound, we do the exact same reaction, and we just simply do it in an aqueous environment. So in the same way that acetal reactions are reversible, right, and I'm not going to show you the reverse reaction of an acetal, but you're certainly responsible for knowing it. Same thing with transesterification. So we can make the ester, right? In this case, losing water, and then likewise, we can do the reverse by adding water. Okay, so that should make sense, right? All these reactions are reversible, thus it simply has to be driven by something, driven by, in this case, the sort of excess of methanol in the presence of water. Certainly you can imagine similar things like we discussed previously, whether it's using a Dean-Stark apparatus, for example, to get rid of the water, molecular sieves. And again, in the verse process, what we would simply do is have a large excess of water, and we should be able to drive this process. Okay, so that's one way that you can make esters. Okay? And again, mechanistically, it should look very analogous to acetal formation. Now, another way that we can make esters is really a two-step process. This is going to be a little bit more than making esters, but it's really a derivation of carboxylic acid to generate a pretty good electrophile, and that's the synthesis of acid chlorides. And so last semester, one of the reactions that we saw, right, was that if you take, say, for example, you take an alcohol, right, and you treat the alcohol with thionyl chloride, what's the product that we're going to generate? Right, the chloride. So instead of having an OH, what we're going to have is the chloride. Sometimes you see this done with a base. We actually run it upstairs a lot. We don't use a base. We just use the thionyl chloride as a solution, and it's fine. But you can use a base in this reaction if you want to. And sometimes, and yeah, I'm not going to use the base in this. So we'll just do it thionyl chloride by itself. And again, from a mechanistic standpoint, right, what's going to happen is thionyl chloride's a little bit weird. Now, I don't want to say weird, but it's a little bit different than what we've seen previously with additions into carbonyls. Generally, when we attack carbonyls, we are sort of breaking the weaker bond in that species, right? And the weaker bond is generally the pi bond. So oftentimes what we're doing is we're adding in the same way that we did, say, for example, here, right? We're oftentimes breaking the sort of double bond. Again, that could be part of the reason why it doesn't go through the other sort of mechanism. This isn't super important, but oftentimes in the literature, I historically would always treat thionyl chlorides in the same way that I would treat any other carbonyl. And so when I would draw mechanisms to thionyl chloride, I would have it go up into the oxygen. I guess technically that doesn't need to happen with sulfur for reasons that I'm not entirely sure about. It could have to do with the fact that this molecule doesn't actually look like this, but it looks more like this inherently. right? So in the same way that phosphorus-oxygen bonds can be phosphine oxide, so we actually never actually have a true negative charge, or sorry, we don't have that sort of carbonyl-like character to it, it's more single bond-like. So generally in this chemistry, what you can actually do is just treat it similar to, say, an SN2 reaction, where you attack the sulfur and simultaneously break the chlorine bond. Right? And when you do this, so this is just to be a bit of a refresher. Might look a little weird there. We've got sort of two positive charges right next to each other. It's probably one of the reasons why I didn't want to draw it that way previously. But again, what can happen here, there's a few different sort of mechanisms that you could do at this point. You can imagine, say, for example, proton transfers over here. I'm not going to worry too much about that because I think it's clear that we have a really nice leaving group there in terms of that cationic oxygen. Right? And so what we'll do is we'll simply attack this molecule. Right? We'll get the chlorine R group, and then as a byproduct, we will end up with. Now again, the mechanism is a little bit more complicated than this. And when you look at this molecule here, it turns out that when you run this reaction, that's not a stable complex. It, in fact, will break down. It'll generate basically SO2 gas. Again, there's a couple different ways you can draw this, but this is the sort of general idea is you generate SO2 gas. And again, there's a few different ways you can draw it, but that's at least the general idea of how the bonds are forming and breaking. Okay, so this is cyanochloride chlorination, and it turns out that you can do a very similar mechanism or similar reaction with carboxylic acids. Okay, and so let's go through the mechanism of that very quickly. So again, this is a very valuable reaction. You guys have seen this a lot, particularly in synthesis problems, right? Because alcohols, you guys know ways to make alcohols. We actually just discussed some ways to make alcohols. And certainly having that versatility to take an alcohol, right, and turn it into a chloride has that ability to, turn it into a really good electrophile, which can make a lot of new bonds, right? Halogens are very, very versatile. Okay, and as it turns out, acid chlorides are also very versatile. Okay, and so if you take these molecules and you treat them with thionyl chloride, again, the mechanism is going to be analogous in many ways, except for the fact that we're not going to have it attacked from the OH, right? We'll have it attacked from the carbonyl, right? And so if you sort of follow that first step there, really what's going to happen, right? Just as we've seen previously, right? Is we'll get to a species that looks something like this, right? And again, there's a few different mechanisms that you can imagine drawing here. But we have that chlorine. Again, we have this decent leaving group here. We can sort of add in. Okay. Again, at this step, what we can do is break down this sort of penyacetal. Again, I'll just directly show the degradation, generate the SO2. Right, and now what we have is with the chloride, which can simply deprotonate that and get to our rock. Okay, so again, it should be very analogous, and really the only difference here is that you have to recognize that the carbonyl oxygen, right, this oxygen up here is going to be the better nucleophile in this chemistry, so you just want to start by attacking sort of at that position. Okay. Now, once you have these acid chlorides, again, in the same way that alkyl chlorides are very versatile, it turns out that acid chlorides are versatile as well. There's lots of nucleophiles that we'll see that we can treat them with to make lots of new bonds. So certainly if you take an acid chloride and you treat it with, say, for example, an alcohol, ROH, methanol, I'll just say ROH. This is R1, this is R2, OH. Right, what will happen is we will get to alcohol. Okay. In the same way, if we take these molecules and treat them with, say, for example, amines, right, we can now make amides. Let's say R2 and H2. Okay, so if we take these acid chlorides and treat them with amines, we're going to get amides. I've just shown it in terms of a primary amine. Right? Again, you guys should be able to do these mechanisms. Simply add in, come back down, take out the chlorides. These are reactions that you guys should be able to do. You can also actually to convert these into molecules known as anhydrides. So we learned about making acetates, right? So it turns out that if you take these molecules and you treat them with, say, for example, a carboxylate, okay? In this case, what you're going to get to is a functionality known as an anhydride. Okay? So it's basically an oxygen linked to two carbonyls. Okay, so again, that's an anhydride. And the other thing that we can do is a way to make actually ketones. So you guys learned Gilman reaction last semester, hopefully. Yeah. Okay. So it turns out that you can take acid chlorides and you can treat them with Gilman reagents, which is the cuprates, right? These QEs, right? So R2CuLi. Again, we'll learn a little bit more about palladium catalyzed and metal catalyzed coupling reactions. Mechanistically, this is very analogous. Just as a sort of refresher, these cuprates are fantastic. Nucleophiles, in a way, they don't behave necessarily in the same way that we classically think of nucleophiles. But they will do chemistry in instances where other nucleophiles won't. Say, for example, a vinyl halogen, right? You can't take a nucleophile and displace an sp2 halide, and this is one of the advantages to something like a Gilman reagent. So it turns out that in cases like acid chlorides, there is that analogous reaction, in which case we can, in principle, make ketones. Okay, so again, acid chlorides, very, very valuable. All right. So we'll discuss one more reaction, carboxylates. Okay, so again, these are all just sort of functional, yeah. Yeah, I mean, this you don't have to. The QE, I mean, you could just treat it as a standard nucleophile, but it doesn't actually behave that way. We'll learn a little bit about more later on about transition metal catalyzed cross couplings, and I think this is more analogous to that, which we haven't actually discussed the mechanism for. But certainly this, and this, you should be able to know the mechanism for. Yeah. So what would a Grignard do in this case? Yeah, you might get away with getting... This is one of those things that can be challenging. So the question is, wouldn't a Grignard do the same thing? And technically a Grignard, you can sometimes get lucky with acid chlorides and get it to add in, because technically in many cases, because the issue comes down to aldehyde, right? Like once the chloride leaves, right, now you got an aldehyde. And the question is, what's more reactive, an acid chloride or an aldehyde? And so there are instances in which case, you know, you're sort of on this, towing this line there. And so generally I don't teach that, but you could argue that an acid chloride would be more reactive than an aldehyde, because it's really that competitive reaction that you're discussing. Oh, sorry, the ketone. Sorry, take that back. Right, the ketone reactivity versus the chloride. Yeah, so I guess that would probably be okay. Yeah, so the question is, yeah, so sorry, my bad. I was confusing it with LAH. So in this case, yeah, you would get the ketone, and the question would be, would the Grignard react faster with the ketone than the acid chloride? And it might, right? It would be a sort of question of relative rates. And so I guess if you made the argument that a Grignard could also do this, yeah, I don't know. I don't generally see that in the literature that much. And I assume that it's because it's not that easy to control double addition. Whereas the cuprate, you'd have an easier time doing it. So the book might, I don't know if the book says that you can do it or not. I definitely think I've seen it. But again, what you're dealing with, again, is relative reactivity. So I would just stick with the cuprate if I were you. But again, I guess you could make the argument that a Grignard might work. But again, it would come down to the question of what's more reactive, the ketone or the acid chloride. And I think you can make the argument that the acid chloride is going to be more reactive. So, but again, I don't see that reaction run too much in the literature. Did I see a hand up over here? Mm-hmm. No, I mean, acid, so what was brought up was saying that a Gilman is a better nucleophile than a Grignard. So here's, I'm just going to show you guys one thing that sort of, when I think about Gilmans and Grignards, since we're sort of on this topic, going back to Orgo 1, and let me just put Gilmans and Grignards from how I view them in terms of how I think about them. Grignards, I always treat as alkyl, like similar, more mechanistically similar to something like an alkyl lithium, right? I think about it as an associated bond, a carbon negative charge, right? So when I think about a Grignard, I think about it more as a dissociated bond, much in the same way that you would think about something like an alkyl lithium or something like that. An alkyl cuprate I think about as much more as being a sort of covalent bond, and in fact the chemistry that takes place from them, again, like I said, you could perhaps draw it in the same way that you could draw something like a Grignard and think about it in the same dissociative way, but it actually involves, I'm pretty sure in principle, more transition metal, because if you look at where copper is, right, it's a transition metal, and so it behaves through more transition metal-based mechanisms, and we'll discuss those later on, and maybe what I'm saying will start to make sense when we start talking about palladium-catalyzed cross-couplings. For your standpoint, I think that it's important to recognize from a mechanistic standpoint, right, that when you have something, and again, when we talk about palladium-catalyzed cross-couplings, this will make sense as well. If you take something like a vinyl bromide, right, and you were to treat it with a standard nucleophile through these substitution type mechanisms that we've seen in the past, right, you cannot do this. This will not work. You cannot take a nucleophile and treat it with an sp2 hybridized carbon, right? But you can with a Gilman, again, because it doesn't go through substitution-like chemistry. Gilman reactions go through more transition metal-like chemistry, and so it's not this type of mechanism. We can reason it in this type of mechanism for now. Hopefully it'll make more sense once we discuss the mechanism of transition metallized chemistry. So this will work if you want to, say, use a cuprate, right? And so in general, when you have alkyl halides, honestly, it's probably best to just go right for the Gilman. The Grignard, usually people use Grignards for reactions with things like ketones. Like, it's very common for people to do chemistry on aldehydes and ketones with Grignards. It's not that common for people to do simple substitution chemistry with Grignards. The great sort of complementary nature of Grignards where you begin to see a lot of complementary nature in sort of Grignard-Gilman chemistry really comes when we start talking about things like alpha beta unsaturated carbonyls. Okay. I was trying to put on too much of a tangent here. This is stuff that I generally teach in Organic 1, so I guess we're just sort of revisiting that. But when you look at this sort of alpha beta unsaturated carbonyl, and we start to think about where the delta positive charge is, right? If we were to take this molecule and we were to treat it with a nucleophile, there's actually 2 carbons on this molecule where you can imagine that charge would be. Right? The first one, we just think about this resonance form. Right? We have the carbonyl one we discussed the last couple classes, right? So we've got a delta positive here. Okay? And we've also got a second resonance form in these conjugated systems, right? And that's when we move that double bond. Okay? When we move that double bond over, now we put the positive charge here. Okay? And so what we have is really a second electrophilic site in these alpha beta unsaturated ketones as well. My first exposure to cuprates and Gilman type reactions actually was differentiating between whether a nucleophile is going to attack here or whether a nucleophile is going to attack here. Because as it turns out, if you take an alpha beta unsaturated ketone, such as in this case, this sort of vinyl methyl ketone, right? And you treat it with, say, for example, methyl magnesium bromide, the product that you're going to get after workup is going to be the alcohol. If you do the same thing with, say, for example, methyl cuprate, what you get is addition there. Okay, so you're basically making that bond. Again, it's going to go up to the enolate, which will go back down and punch it. Now, why is this the reason? This is actually going to be the first class in my advanced organic class that I was, or one of the first classes that I was going to teach in the advanced organic class. It's a little bit more complex. It involves these concepts of hard, soft interactions, and how a Grignard is considered. Again, we discussed how it's more ionic in character. If you were to actually look at where the charge density distribution would be, the part of the molecule that has the most positive charge to it is actually this carbon, again, because it's closest to the nucleophile. So this is where the biggest delta plus is, right? So the molecule that's more charged would actually react here. But in terms of molecular orbital theory, in terms of thinking about where what we call the sort of the sort of lowest energetic state within the molecular orbital. So when we're thinking about energetics and where the sort of LUMO is in this conjugated system, this happens to be the sort of lowered energy site for that reaction. And in these instances, when you have a not so charged nucleophile, they will in fact attack here. So again, I just went on a huge tangent. Sorry. So that's really kind of oftentimes when I think of it. Yeah.
I'm curious. Was that long that you do with this double bond or single bond between? What is the less reaction?
Yeah, no. So you can't. Yeah. So if you try to treat a cuprate, so the question is, yeah, you need this conjugated system. So the question is on something like this. Yeah, no, because it's not conjugated, right? You can't draw that same resonance form. So, all right, let's get back to material here. All right, carboxylic acids. So how do you make carboxylic acids? Well, we just discussed one way, right? You can basically take an ester, for example, and you can generate, you can just hydrolyze it. But again, that's maybe not too big of a change, right? You actually have to have the ester, and then the question becomes sort of how do you make the ester? So ways in which case you can make carboxylic acids through carbon-carbon bond forming reactions would actually be very valuable. And we actually have a couple different ways that we can do this. Okay, the one way is that if you have, say for example, a alkyl Grignard or an alkyl lithium, for example, one of the ways that people are able to take these and convert these into carboxylic acids is actually to take these molecules and treat them with carbon dioxide. So this is one way that we can actually make carboxylic acids. Again, the reaction would simply involve attack of that anion to the CO2, right? And what that's going to get us to is the carboxylate, and again, then you would simply treat this under acidic conditions and get the carboxylic acid. And so this is one way in which you can make carboxylic acids with, while simultaneously making a carbon-carbon bond. And this would come from nucleophiles. We can also do a similar type of reaction, but it's going to take an additional step, but I'll sort of introduce it now. If you want to, say for example, so again, this would be following workup. So this would be from nucleophiles. You can also do it from an electrophile as well. It's going to be a two-step sequence. So from electrophiles, so if you have something like an alkyl halide, right? So let's say this is an alkyl bromide, for example. Really what we want to do here, right, is we want to kind of add in something like this, right? Can't do that. It's not a why, I don't know, that's not a species that exists, but formally that's what we want to do. But there is one specific really good nucleophile that's actually oxidative equivalent, if you will, of this type of species, and that's cyanides. Okay, so instead of 3 bonds to oxygen, right, you have 3 bonds to nitrogen, right? This is a really good nucleophile, right? Certainly something you can generate. And so if you use some type of cyanide-containing molecule, lithium cyanide, sodium cyanide, what's going to happen is you're going to get the carbon-carbon bond in this case, right? So now you've got to sort of see it. And then what you have to do is you simply have to take this molecule and you have to convert all those carbon-nitrogen bonds into carbon-oxygen bonds. Anybody have an idea of how we might, we haven't learned this yet, anybody have an idea of how we might do that? Yeah. Acid N, that might start the process. Yeah, so something that's going to provide us those, right, that oxygen. So an acid is going to catalyze this process, but we need something that's actually then going to come in and make the bonds. And so if the first step is cyanide, the second step will be, just like you said, acid and water. Okay? If you take this molecule and treat it with acid and water, what's going to happen is you're going to get to carboxylic acid. All right? So from a mechanism standpoint, this is going to be a process. I guess we have time, I'll go through it. But as I'm going through it, I want you guys to be one step ahead of me. So start trying to figure it out while I erase this side of the board, and then we'll go through it. Again, it's going to be very analogous to transesterification. So ask yourselves, as I'm erasing, what is the most if this is our acid, right, what's the most, and we want to sort of catalyze this process, and we've got the water, and we're trying to do this analogous to what we've seen in the past. Well, previously we saw protonation of a carbonyl. We don't have a carbonyl here, we have a carbon-nitrogen bond, right? Does the carbon-nitrogen bond have the ability to perhaps be protonated? Yes, it does, because it has those lone pairs, right? And so, from a mechanism standpoint, if we have, say, for example, CN, right, what can happen is we can protonate. right? And now we've got a pretty good nucleophile, right? And now we can begin to make those oxygen-carbon bonds, right? So what's going to happen is water is going to add in. Okay, just like before, proton transfer, right? Again, this can be reversible and switchable. Doing that proton transfer positive charge onto the nitrogen. Now again, there's probably some other mechanisms we could draw in this area, but you should be able to see right away perhaps a resonance form that's going to start getting us a little bit closer to that product. Right, so now we can actually make that carbonyl bond. Again, you could add water in at this step if you wanted to. I'm just sort of doing this off the top of my head in terms of what's going to get us there. Okay. Again, maybe I would have saved board space by just adding water in directly there. But again, these are just resonance forms or others, so it's the same molecule. But again, we can add water in. I'm out of board space. Okay. Yeah. We're going to get proton transfer out of space. We're going to put a proton over onto this nitrogen, right, and then we're simply going to eliminate ammonia. Right? So what we're going to do is we're going to protonate this. Okay, that's going to put the nitrogen, take the nitrogen-hydrogen bond, let that sink in. Okay. Now at this step where now we have an ammonium, which can be a leaving group. Now we have the right compound. We can eliminate ammonia, and then again, we're simply at a deprotonation step away from the product. So again, you guys should be able to do that on your own. So again, this is just an alternative option for adding carboxylic acid to a molecule. So you could do it from a nucleophile by treating the nucleophile with CO2. You can do it from an electrophile by treating the molecule with cyanide followed by hydrolyzing the compound. Okay. So we can put CO2 on. Can we do the reverse? The answer is yes, we can. Okay. And the ability for a molecule to decarboxylate, again, everything's sort of reversible, right? But you can actually do what's called a decarboxylation. We'll discuss some instances in which it's actually easier to do it. But in standard, you can actually thermalize a lot of reactions. You can actually get them to eliminate. Again, it's at very high temperatures. It probably involves homolytic bond cleavage events. So again, I'll show a mechanism perhaps through homolytic or heterolytic bond cleavage. So just sort of show it, but it might look a little bit awkward to you. But let me just give you an example of a compound that we actually work with upstairs on occasion. We actually don't work on it too much, but this doesn't work that well in our chemistry. So here's a molecule called pyromaconic acid. I know this is kind of interesting, so if something jumps out at you in the name that seems maybe strange, might be the pyro. When you think about pyro, when you think about pyrotechnics and explosions and high temperature, right? And in fact, that's how this molecule is made. There is a molecule known as maconic acid, And literally what this is a molecule that they just take this other molecule and heat the Jesus out of it and make this molecule. So maconic acid so this is maconic acid. And again, to get this to convert to this, they take it to greater than 200 degrees. And basically the molecule decarboxylates. From a mechanism standpoint, how does this work? It's perhaps easiest to think about it. See, this is complicated because when people do decarboxylations a lot nowadays, they use like metals to catalyze the process and stuff. For your guys' standpoint, I'll show you maybe just an easier way to think about it. Maybe I think the best way to think about it might be perhaps in the presence of a base. But again, it's probably more through homolytic bond cleavage events. So let's do it through homolytic bond cleavage really quickly, and then I'll show you guys another way. Okay? So again, I don't entirely know what the mechanism of this is, but from a standpoint of what makes sense to me, the fact that you can actually heat this and you're going to really high temperatures, what that means is that you're probably involved in, again, radical type mechanisms where you're actually doing homolytic bond cleavage type events. Yes? Well, yes, that was where I was going to get to, is you can do it with bases, in which case you have an anion. So we'll get to that in a moment, but you don't need to. You can just heat up to really high temperatures. And again, I think it's probably best to think about it. We'll show both ways. From a homolytic standpoint, it might be best to think about it as perhaps a fragmentation of that oxygen-hydrogen bond. Again, maybe you could imagine a fragmentation over here as well. Now what you have is a radical, right, plus your proton. This is going to generate CO2 gas, right, and then simply all we're going to do is bring the proton and the hydrogen together, okay? And that's going to get us our proton. So this is one way that you can do it, and again, this may be how it takes place in, say, for example, pyromaconic acid. As we just brought up, a perhaps more comfortable mechanism for you guys might involve base-mediated processes. So if you do the decarboxylation under a base, so if you heat it in the presence of, say, base, in this case, you can also generate RH. In this mechanism, what you could do is you can actually deprotonate it first, right? Okay. And now in this case, what's going to happen is now you're doing effectively an anionic based process. So unlike here, where we're, and this might look similar to the Wolff-Kishner reduction, that last step in the Wolff-Kishner reduction, right? We're going to get okay. And again, in that first step, what we've done is we've deprotonated with the base, right? And so now we have H base. So what can happen is we can regenerate the base and deprotonate it. So this would be another opportunity again. Which one you may actually want to do in practice, maybe due to the relative stability, whether or not you can imagine an alkyl radical being stabilized, or whether you can imagine an alkyl anion being stabilized. But again, these are two different ways that you can think about going upon them. There are specific, even within the base-mediated processes, oftentimes what will drive the elimination process is stabilizations of the anions that are formed. So if you have compounds that have really good anion stabilization, this can actually work at much lower temperatures. So say, for example, say, for example, if you have this molecule here, yes.
Does this base also require a high temperature?
Yeah. Well, it depends. It's going to depend how good. Usually, you heat them up. Again, does it always? It's always going to depend upon the substrates and how easy. But yeah, if you just wanted to take an alkyl group and get it to eliminate, yeah, you probably need to. Again, I was reading a paper recently because we've been interested in decarboxylation chemistry in our research, and we were looking at like, they're talking about low temperature decarboxylations, and they're saying low temperatures, and it's like 110, right? So that sort of puts it into perspective, and that's catalyzed by like copper and stuff like that. So even if it's just a little bit of heating, not necessarily pyrolysis, sometimes there's often that need for heat. But there certainly are instances. Oftentimes you'll see in the literature it'll be like they don't want it to do decarboxylation, and suddenly they'll get decarboxylation chemistry. And oftentimes we'll be in situations like what I'm about to show you here. If you can really easily stabilize that negative charge, sometimes the decarboxylation will be much more facile. Okay. And the reason, as you might imagine, would be that if you treated this with a base, and you go through that same sequence, you can actually sort of have that stabilized phenolate product. Okay, so I guess in the way that I had it drawn, you have the phenolate. Right, and again, this is just a ketoenol monomer. You end up getting the ketone at the end of the day. But again, you could probably do this at much lower temperatures. To give you some numbers, again, previously I talked about, just to put it in perspective, previously I was talking about heat assist. You can actually do this chemistry even without a base, as long as you can get the appropriate orbital alignment. Without base, it's kind of neat. We'll see this a little bit later on in the chapter, this sort of idea of sort of 3 arrows in sort of a 6-member transition state. But you can imagine if you can redraw this molecule, and I'm just going to rotate around this bond, what we have is that molecule there, okay? And so you can actually do this without base, you can do this thermally, and it will work at what I have written down, like 150 degrees. So again, it's from over 200 to about 150, so it's still thermal. But what's interesting in this case is that now you can go to the enol, and it's a 6-electron process. And so this is something that we'll see a lot in Diels-Alder chemistry, for example. Moving 3 electrons, there's this sort of, you guys know the chair, right? Chairs, the 6-member chair transition states are really stable. So there's a lot of chemistry that we're going to, and we'll see some later on in the semester, that involves this sort of 6-atom process where they sort of line up in that chair, well, sometimes it's chair-like, but in that sort of form. And again, in this case, now what we get to is the enol plus CO2 gas. So generally, this is a thermal process. Sometimes there are instances where the orbitals align, I guess, such that things like this can happen at sort of lower temperatures. But generally, they are thermal processes. Okay. All right, I'd like to discuss, so this is good. So next class, we got about 10 minutes. And I'd like to be done with carboxylic acids at the end of this class. So we talked about acid chlorides. So let me just, so I feel like I'm backtracking a little bit here. But I do want to make sort of one point, because everything that I try to teach you guys here has sort of been at least fluid in terms of one thing connecting to the next. So sort of reset yourself and imagine that we're back and we just learned about reduction chemistry. And again, in the case of carboxylic acids, we discussed esters a little bit, right? So we know that things like carboxylic acids aren't going to be reduced in the presence of sodium borohydride, right? You need a much stronger reducing agents. So if you want to reduce a carboxylic acid, you can certainly use LAH. This process is a little bit, and again, you're gonna end up at the alcohol. One of the interesting things about carboxylic acids, though, is that oftentimes the go-to reagent is borane. I don't know if your book discusses this, but BH3 is often used as well. Again, it's kind of an extra reagent that does the same thing, so I don't really think it's too important. I'm not going to test you on BH3, but you may see it in your book. Again, there's mechanistic similarities to the LAH reaction, but again, because of the fact that we have that carboxylic acid there, you know, previously this was sort of protected from breaking down because it was an ether. In the case of the carboxylic acid, you take the C3 fluorine. It's also going to go all the way down to the alcohol. So I think it's redundant to sort of show you this and this, but this is often a reagent that people like to use a lot in sort of synthesis is borane. But again, to get to the borate, so that you have that negative charge, it can behave as a hydride. You can imagine the first step is going to be activation. So anyways, this is just sort of refreshing a little bit. These aren't going to work with sodium borohydride. They're not going to work, I don't think they work with platinum and hydrogen. At least that's what I wrote in my notebook. But there's a couple other derivatives, I think, that we should discuss. And that's some of the derivatives that we discussed previously. So if we have, say, for example, a nitrile, this is another reagent. Again, we saw previously how you could do a reductive amination to generate amines. In the same way, if you have a nitrile and you treat this with lithium aluminum hydride, you can also sort of reduce to the amine. So if you take this molecule and you treat this with LAH, LiAlH4, it's the same thing. So these are the same. This is just a reagent. This will go down to the primary amine. Okay, so that's one thing that you might see from time to time. So again, that could be useful if you're trying to make an amine. Again, we can make that carbon-carbon bond with the cyanide, and then simply reduce it down to the amine. Another way that you can actually make amines as well, though. Again, I'm not really sure how useful it's going to be for you guys, but you know, it's one of those interesting things, I think, and that's that if you have an amide. I'm not sure that you're necessarily, I mean, yeah, this could be useful. I'm sure it's useful, but what's I think interesting about this case in terms of the amides, and one of the things you'll want to remember, because you look at these molecules and you go through the mechanism, and I think it might be confusing to be like, well, I can imagine it generating the alcohol, and I can also imagine it generating the amine, and as it turns out, it generates the amine. And unfortunately, I don't have a real great way for you guys to rationalize why it does that. I was trying to come up with an explanation that would sort of make sense for you guys. But this is what it does, so I apologize for not having a great explanation for that, but it's just sort of worth noting that if you have the amide and you treat it with LAH, what you will get to is, in fact, the amine, the same thing that you would get if you have the nitrile. Okay, so just one more thing. And that is going to be just a quick, again, I'm not a big nomenclature person, but there are certain names, and so we've discussed a few different things in terms of esters, aldehydes, and so forth. There's a few others that we didn't actually get to, and I think it's worth sort of mentioning right now. Again, these are amides, as we discussed before. There's two things that we'll see. So if you have, say, for example, like an ester, just some terms you guys should get familiar with. If you have an ester and it's actually cyclic, right, it's sort of a cyclic ester, you might want to call it. There's actually a technical name for this, and it's called a lactone. And there's significant reasons why we differentiate. We don't just call this a cyclic ester because, as it turns out, lactones are actually much more reactive than, say, esters. And again, we can discuss that at some other point if you're interested. And the other thing would be sort of cyclic amides. These are considered lactams. So some of you guys have heard of like beta-lactam antibiotics, for example. You'll sort of look at the structure and you'll see those are four-membered cyclic amide, if you will, in there. Okay, so I have one quick announcement. So again, start getting ready for the upcoming quiz. I have to sit on a thesis committee thing today, and the only time that they could make it work was at 11, but we're going to try to get done by 12. So I'm not going to be available at 11, but I'll hopefully be back in my office by 12, in which case I'll stick around until about 2 or so for office hours. Okay. 4:37.